Okay, 11.6 and integration by parts. Now, in earlier videos we've said, well, we don't have a product rule for integration. Wouldn't it be nice if we had a product rule for integration? If you think back to the differentiation chapter, we have a product rule and a quotient rule, but the quotient rule is just a rearranged version of our product rule, right? So if we have a product rule for integration, then we can integrate products and we can also integrate quotients. So that'd be great, right? One rule will do. If we don't get a separate quotient rule, then that's fine. We can just use the product rule. If we're trying to integrate something divided by something, we can rewrite it as the integral of u times v to the power of minus 1, and then we're away. So I don't know, if we're trying to integrate sine x divided by e to the x, I could rewrite that as sine x times e to the minus x, and now I've got a product of functions. So if I've got a product rule for integration, then we're away. What we have is a thing called integration by parts. So when you hear the words integration by parts, you think that's the product rule for integration. If I have a product of functions, I use parts. And depending on your point of view, this is either a really neat little trick that we use, or it's a really annoying sort of either you think this is super clever or you think it's just sneaky, but it works like this. The derivative of a product is our product rule. So I can rearrange this product rule, and I can stick this bit over this side. So I can say u dv by dx equals d by dx of uv, that bit, and I'm taking this away, so minus v du by dx. Okay? Now what I'm going to do is I'm going to integrate this side and I'm going to integrate this side. So integral of u dv by dx equals, well, the integral of this with respect to x is uv, minus the integral of this bit, which is v du by dx with respect to x. Okay, and you're thinking, okay, well, that's a nice horrible mess. Now what? Well, now what is our integration by parts formula. Looks hideous, but this is how it works. Look, the integral of this times this. Well, this is a function and this is a function. So this is a product of functions. So the integral of a product of functions is what we wanted. And what have we got? Well, we've got that it's this times this minus this times this. And you think, well, that's useless. This is a product of functions, and you've told me that it is some functions times together take away a different product of functions. So it doesn't seem as though it's going to be very helpful, except let's look a little bit closer. Here we've got u, here we've got dv by dx. Here we've got v, here we've got du by dx. So if I can differentiate u, I can find this bit. If I can integrate this function here, I can find this bit. At no point do I have to integrate u, and at no point do I have to differentiate this function here. So if I can deal with these two functions separately, if I've got one of them that I can integrate and one of them that I can integrate and one of them that I can differentiate, that's good enough. I can do the integration by parts. So I can't necessarily do any product, right? It has to fit certain rules, but at least I can shuffle around my product. Now we're still going to have an integral to deal with over this side, and we'll find out that sometimes the integral we've got left to deal with over this side isn't going to be easy to deal with. But for the questions that we're going to deal with on the A level, this integral is then going to be something which we can evaluate. Okay? If you go a little bit further, you find that sometimes this integral is not one that you can evaluate, but then there's something else that we can do with it. This is still an integral by parts, and we can we can use the parts formula again and again, and we can end up with something that will work. I'm not going to get into that because it's not something that we need for these particular questions. Unless I've made a mistake, I don't think we need to do that. But well, if we do, I'll find out as we hit the examples. This is still a fairly new textbook, so I'm not double checked, which perhaps is foolish, but we'll see. So here we go. This is my product of functions. This is my parts formula. Integral u dv equals uv minus the integral v du, and then I chuck my dx's in. So that's the way I remember it. U dv equals integral of u dv equals the integral of uv minus the integral of v du, and then you need dx's sort of everywhere. Okay, but that's the sort of rhythm that I say it with in my head. Uv minus the integral of v du. So our first choice is which one of these functions is going to be u and which one of these functions is going to be v. Well, what we're going to say is the function which you can differentiate and it will eventually disappear. So the polynomial function is usually the one which you want to let be the u. Now there are some exceptions, but usually if you've got an x or an x squared or an x cubed, let that one be u, all right? So u equals x. Oh, and the other thing is there's only two choices. So try it one way. If it doesn't work, try it the other way. So u is x. dv by dx, which I'm deliberately writing down here, by the way. dv by dx is cos x. I've got a product of functions. That product needs to be written like this. So I now need to find du by dx, which I can do. Derivative of x is 1. And I need to find v, which I can do. The integral of cos is sine x. I'm not going to worry about the constant of integration, by the way, because we'll pick that up when we integrate this one. We'll stick a constant on the end of it. So we don't get confused, I'm going to call that integral I. I've done a bit of working out, and now I'm going to say I, the integral I started with, is equal to uv, so that is that times that, x sine x, minus integral of v, which is sine x, du by dx, which is 1. And we've got this. Well, so what? We haven't finished the integration, but hang on a minute. We're integrating sine x. Now that is not too bad. The integral of sine x is just minus cos. So that minus sign becomes a plus and we get a cos x in there. And now we stick our constant of integration on, and there is our answer. So we started with that, using this ridiculous formula. Everything pops out nicely and it works, okay? I'm going to do one more example just to show you the sort of rhythm of it and the way it works. If you don't want to follow this example, then that's absolutely fine. If you feel like you get the idea, just fast forward. I would recommend you looking at example 19, which I'll be getting to in a couple of minutes though. Okay, so we're going to say u is the x squared. dv by dx is the natural log. Okay, that's what we just said. We just said, well, we tend to let the polynomial bit be that, except we haven't got a way of integrating natural log. Okay, so when I say we tend to let the polynomial bit be the u, the exception to that rule would be I need to be able to integrate this one, I need to be able to differentiate that one. I can't integrate that one, I better make that be the natural log. So in this case, I'm going to swap that rule around, okay? So that's why this particular example's there. As a rule, it's a good idea to let the polynomial bit be the u. If you can't integrate the other bit, then let the polynomial bit be here. So du by dx is 1 over x. The integral of x squared is x cubed over 3. By the parts formula, so the integral of, well, I better write this out, hadn't I? Integral of udv is uv minus the integral v du. So that's my integral. My integral equals u dv, sorry, uv, which is that one times that one, isn't it? Oh, got to be careful with this formula. It's a fiddly formula, easy to get it wrong. Natural log of x times 1/3 x squared. It's 1/3 x cubed even, oh my goodness. So 1/3 natural log of x, x cubed. Take away the integral of v, which is this one. du by dx. So we get, I'm going to write this more sensibly now, 1/3 x cubed natural log x minus, bring the third out the front of the integral sign, integral x squared dx. That is 1/3 x cubed natural log x minus 1/3. X squared integrates to 1/3 of x cubed and then don't forget the constant. Okay, and that obviously would be neater if we wrote that as 1/9, and there's my answer, okay? You'll notice there are 4 examples here, and they're each showing you one of the kind of things we can do with integration by parts. So example 16 is the most straightforward. We let the polynomial bit be u, the other bit is the x, and it works straight away. The second bit in example 17, we wanted the polynomial bit to be u, but when we try and let x squared be u, the natural log has to be dv by dx. We can't integrate the natural log, so that was no good. So we have to swap them around, and that was fine. Now the next one, example 18, x squared e to the x dx. Now this is an example that I mentioned a while ago, saying that we don't have to do this much, but this is the thing that I think we maybe would get away without doing. This is a sort of nice-ish version of it. Du by dx down here, v up here. So here we go. Derivative of that is 2x. dv by dx is e to the x. Integral of that is e to the x. So by parts, we get our integral is uv minus the integral of v du by dx. And we get x squared e to the x minus 2 the integral of x e to the x dx. And we've got a problem because we don't know what the integral of this thing is. But it is a product of functions. So I could probably just apply parts again. So just dealing with that bit, we get u as x, du by dx is 1. dv by dx is e to the x, v is e to the x. So the integral of this bit is going to be uv x e to the x minus the integral of v du, and that is x e to the x minus the integral of this thing, which is e to the x. Okay, so all of that, we can change this bit here. So our integral I becomes x squared e to the x minus 2 lots of x e to the x minus e to the x. And there's my integral done. Okay, I'm going to have to mess around and tidy it up a little bit, but that's the idea. Now you might think, well, that's a pain, we've got to do it and then we've got to use parts again. But actually, as parts go, sometimes you end up with something here that you can't integrate, and then you do it again and you end up with something else that you can't integrate. You maybe have to use it a couple of times round, and then there are fiddlier ideas with it. So we're still spared the really nasty one, but that's the third kind of question you can get with parts. You let u be the polynomial bit, but you have to use it a couple of times to make the polynomial bit properly vanish. Not too bad. Now the other really useful bit we can do with parts is this, integral and natural log of x with respect to x. Now, in fact, in example 17, we said, well, hang on a minute, we haven't got an integral of natural log, so we had a problem. Well, what about this? Natural log is 1 times natural log. So I can think of it as a product of functions. Now the cunning thing about this is, I can think of it as a product of functions, and I can let u be natural log of x, du by dx is 1 over x, dv by dx has to be the other thing that's in the product, so that's 1, and v is going to be x. If you look carefully at the parts formula, dx equals uv minus integral of v du, we never have to integrate u. There's u there, there's u there, there's du by dx there. So if I've got a function that I can't integrate, but I can differentiate, one thing to do is to write that function, times it by 1, and use parts. And let's see what happens. My integral, I, turns into uv, which is x, natural log x, minus the integral of v du, which is x times 1 over x, which is the integral of 1 with respect to x. That is x, natural log x, minus x. Don't forget your constant of integration. Okay, So we do now have a way of integrating natural log. The integral of natural log x is x, natural log x minus x plus a constant. And in the question there, you're doing it as a definite integral, so we need to use it a bit further on. So there's our integral of natural log x, okay? And we found it using parts. It's pretty good, isn't it? Now, the other thing I suppose that we should stop and just point out here. No, actually, I'll do it in a separate video. There's an interesting thing on page 209. Okay, so that's it for that one. Good luck with exercise 11F.